Post-training diffusion language models is quickly becoming the frontier for efficient, high-reasoning AI. But there's a fundamental mismatch in how we're currently teaching them. Existing on-policy self-distillation methods were built for autoregressive models. They assume left-to-right generation and token-level supervision. When you force those assumptions onto diffusion models, you hit a hard architectural wall. Today, we're breaking down OPSD, a new framework that finally aligns on-policy self-distillation with the iterative, arbitrary order nature of diffusion LLMs. We'll walk through the exact mathematical shifts required, why suffix conditioning changes everything, and how this approach achieves state-of-the-art reasoning performance using just 10% of the optimization steps required by reinforcement learning baselines. To understand why this matters, let's quickly align on the mechanics. Autoregressive models generate text token by token, conditioning strictly on the prefix. On-policy self-distillation exploits this by having a student model sample trajectories, then using a stronger teacher, or in self-distillation, the model itself with privileged information appended to the prompt, to provide dense, token-level KL divergence supervision. It's highly sample-efficient compared to reinforcement learning with verifiable rewards, which suffers from sparse outcome rewards and heavy rollout overhead. But diffusion LLMs operate completely differently. They don't generate left to right. Instead, they treat text generation as an iterative denoising process. You start with a fully masked sequence, and at each step, the model predicts the distribution for all positions simultaneously. It then unmasks the top K most confident tokens, keeps the rest masked, and repeats until the sequence is clean. This arbitrary order generation is a massive advantage for parallel decoding and speed, but it completely breaks the prefix conditioning and token-level supervision paradigm of standard OPSD. So how do we adapt OPSD to this new paradigm? The first breakthrough in OPSD is a complete reframe of self-teacher construction. Instead of appending privileged information as a prefix, OPSD leverages the bidirectional nature of diffusion models to inject it as a suffix. Here's the workflow. The student model samples a complete trajectory from scratch. Once it generates a final answer, OPSD doesn't just discard it. It takes that self-generated answer and selectively reveals a subset of tokens to serve as privileged context for the teacher. Because diffusion models can condition on both past and future tokens, the teacher can now compute distributions using P of prefix given suffix. This means the student isn't just learning from static reference solutions or environment feedback. It's learning from its own self-generated future experience. It's akin to a researcher looking at their own completed draft to understand the reasoning path they took, rather than just following a rigid template. The second critical shift is moving supervision from the token level to the step level. In autoregressive models, you can calculate divergence between the teacher and student at every single token position. But in diffusion, tokens are revealed in batches based on confidence scores at each denoising step. Token-level supervision is mathematically incompatible with this process. Instead, OPSD treats each denoising step as an independent Markov transition. At step T, the model computes full sequence distributions for both the student and teacher inputs. Then it isolates the top K most confident masked positions, which are the actual tokens driving the state transition from T to T-1. The loss is calculated as a step-level KL divergence strictly over this subset. This aligns the training objective perfectly with the iterative mechanics of diffusion generation. Crucially, the ablation studies show that selecting this top K subset from the teacher's distribution, rather than the student's, yields a stronger learning signal by forcing alignment with the most confident policy paths. Let's get into the implementation details that make this stable and scalable. First, the sampling strategy mirrors PassAT-K for each prompt. The model samples trajectories until it produces a correct answer, or it hits a threshold, defaulting to 8 iterations. This keeps the computational overhead comparable to RLVR's group rollouts. Training stability is another major hurdle. The authors found that per token pointwise KL clipping is non-negotiable. Without it, the divergence contributions skew heavily across the vocabulary, and the model collapses around step 150. With a clipping threshold of 0.05, training stabilizes and consistently outperforms the unclipped variant. They also fix the teacher policy to the initial weights throughout training, which prevents distributional drift and further stabilizes the distillation loop. Memory efficiency is handled elegantly too. Since diffusion models require full attention over all token positions at every denoising step, storing gradients for a full trajectory can easily cause out-of-memory errors. The solution: concatenate the input states across all steps of a single trajectory into one large batch tensor. Because the model weights are shared across steps, the gradient computation becomes constant and doesn't need to be stored redundantly, slashing memory overhead without sacrificing accuracy. The results speak for themselves. Tested on LLDA 8 billion across mathematical reasoning and planning tasks like GSM8K, MATH500, Countdown, and Sudoku. OPSD consistently matches or exceeds both supervised fine-tuning and RLVR baselines like Diffu-GRPO and VRPO. But the real story is sample efficiency. Where Diffu-GRPO requires thousands of optimization steps to converge, OPSD hits peak performance in roughly 10% of those steps. Even with a PassAT-K of 1, it still outperforms the RLVR baseline that uses 8 rollouts per step. Why does the suffix conditioning outperform the ER-style prefix approach? The authors introduce a metric called overlap top K, which measures how much the teacher and student distributions actually agree at the masked positions. When you append a static reference solution as a prefix, the overlap is nearly 100%. The teacher isn't providing new information, it's just repeating the ground truth. With OPSD's self-future suffix, the overlap sits in a much healthier range. The teacher is actively injecting novel thinking patterns and reasoning paths that the student can actually learn from, rather than just memorizing a fixed template. No framework is perfect. The authors transparently document a failure mode common to both RLVR and OPSD. Policy collapse after peak performance. Once the model gets too confident, the model-seeking behavior of reverse KL divergence becomes overly narrow, preventing further exploration and causing catastrophic degradation. This isn't a flaw in OPS specifically, but a fundamental challenge in on-policy distillation and reinforcement learning that future work will need to address. There's also a subtle trade-off with the teacher's retaining ratio. A higher ratio makes the teacher stronger, but the experiments show that a moderate ratio of 0.25 actually outperforms a high ratio of 0.5. This suggests that distillation effectiveness isn't just about teacher accuracy. You need enough noise or uncertainty in the teacher's guidance to force the student to generalize, rather than just overfitting to a perfect solution. OPSD represents a necessary paradigm shift. By aligning on-policy self-distillation with the actual mechanics of diffusion language models, it unlocks dense, step-level supervision without fighting the architecture. It's faster, more sample-efficient, and fundamentally better at transferring reasoning patterns than legacy ER-style distillation or sparse reward RL. If you're working with Diffusion LLMs or exploring post-training techniques for next-generation reasoning models, this is a blueprint you need to understand. The code is open source, and the implications for scaling efficient, high-reasoning AI are substantial. I'll leave a link to the paper and repository in the description. If you want to dive deeper into the math or run your own ablations, check out the full breakdown in the pinned comment. Thanks for watching, and I'll see you in the next one.